Hello, everyone. Welcome back to AAS Publishing and on this APJ Author Series. And I am absolutely delighted today to have Katelyn Breivik with us. So, Katie, you want to say a little something?
Yeah, thanks for having me, Frank. I'm Katie. I am a postdoc at CETA, which is the Canadian Institute for Theoretical Astrophysics in Toronto. This is part of one of 3 units in Toronto, so it turns out many people may not know this, but there are something like almost 100 astronomers up hanging out in Toronto under the University of Toronto Department of Astronomy and Astrophysics, the David A. Dunlap Department of Astronomy and Astrophysics. Then there's the Dunlap Institute, and then CETA. So there's a bunch of us up here.
Very cool.
Yeah, and I am excited about all things binary stars, and I'm excited to chat with you about this paper that we're going to talk about.
Binaries. So let's just go to it. So in fact, this paper is about binaries, and we're going to be talking about, I'll do a screen share here.
Cool.
So we get this up, and we are going to be talking about constraining compact object formation with 2M0521.
Yes.
Take it away.
Okay, so this paper is sort of one that I think of as being the second in a series of papers that I've been working on with, at first, Saurav Chatterjee and my thesis advisor, Shane Larson, and then we looped in Jeff Andrews. All of us sort of have crossed paths at Northwestern at one time or another. And this is sort of a little growing field of us who are interested in studying compact objects, but not from the traditional ways that we normally think about studying compact objects in binaries. So here we're targeting wide binaries that will be observable not through something like X-ray accretion or emission of gravitational waves, but just through astrometric wobbles that you see of a bright star orbiting a compact object. And so this paper focuses on one specific source, 2M0521. The 2M comes from 2 mass. I learned that as a theorist.
I was wondering what that was. Oh, got it. Okay, 2 mass.
Yeah. So this is a black hole candidate that was found by a group of astronomers at Ohio State, the Ohio State University. So this is sort of a follow-up to a paper led by Todd Thompson, which is the result of this sort of observing campaign that was, I guess, dreamed up mostly by Todd Thompson and Carlos Badness. And the idea here is you take radial velocity data and you sort it by velocity acceleration. So you just look for the biggest changes in radial velocity that you can find in the Apogee data set. And they did this, then they cross-cut through 2 mass data to get photometric variations, and out popped a giant star that was very obviously orbiting something in a roughly 80-day orbit, but we don't see anything that it's orbiting. So this is a standout candidate for some type of compact object.
Is there a mass estimate on that secondary?
Yeah, great question. So if you actually scroll down to table 1, we summarize the findings in the 2M0521 discovery paper.
Okay.
So these are the observed parameters that we actually get from data you can see are measured very, very well. It's a almost perfectly circular binary, so it's probably circularized through something like tides or Roche overflow mass transfer. Since it's a giant star, tides actually works pretty well to circularize these things.
That's some pretty impressively small error bars.
Yeah, they did an enormous amount of follow-up on this thing. If you look at the, I think it's a science paper, maybe a nature paper. I'm not really sure. It's a fancy journal, but if you look at the supplements, there's like 50 pages of supplements because they worked really, really hard to nail this thing down.
Cool.
Yeah, so the derived parameters that Todd Thompson's team came up with are a giant star with a mass of something like 3 solar masses and a compact object mass with something like 3 solar masses. So this is notably, as somebody who thinks about compact objects and simulating populations of compact objects, This immediately stuck out to us because it is right smack dab in the lower mass gap, the mass gap between neutron stars and black holes. So this immediately stood out to me and Saurav and Jeff as something that would provide really strong constraints on our population synthesis models.
Right.
Yeah.
Okay, cool. So what do you use for your PopSyn?
Great question. So I spent my whole thesis trying to work with population synthesis codes. And as most people who do binary population synthesis, I came up with my own. So my code is called Cosmic. You can see that right in the first sentence after the first section there. This is a collaboratively developed PopSynth code that is a Python interface to Jared Hurley's BSE code, which stands for Binary Stellar Evolution. We have updated BSE since its first release in 2002 to include many bells and whistles that most PopSynth codes these days that are interested in compact objects have included. This includes things like metallicity-dependent line-driven winds. We have different compact object formation scenarios, different supernova engines, stuff like that. So for this particular study, the main thing that we were looking to point out to everyone is that there are two supernova engines that are widely used in our community. Okay. And these are the rapid and delayed models from Chris Fryer's 2012 paper.
You know that.
And the way that these models are distinguished is how quickly you allow asymmetries in neutrinos or in I'm flubbing here, but basically it depends on how quickly you allow the supernova to explode or not.
Yeah.
And if the supernova explodes in the rapid way, then these have higher energetic supernovae and they lead to more massive black holes. So this produces a mass gap between 3 solar masses and 5 solar masses. And then the delayed model allows instabilities to grow over longer timescales. And so you end up getting a more continuous mass distribution.
Fair enough. Small side topic, since it's a topic somewhat close to my heart. Is Cosmic open?
Cosmic is 100% open developed. We love open development. As a quick advertisement, everybody has their favorite PopSynth code. And the thing that we have really tried to do with Cosmic in particular is to make it easy for people to use. So that means that we have thought a lot about what you do with these types of codes, how you do data manipulation, making sure that you can reproduce your simulations, and making sure that it's actually pretty well documented. So awesome. Yeah, definitely check it out if you're looking to make enormous populations of binaries.
Cool. All right. Oh.
Yeah, and if you want something to exist in Cosmic that you don't see existing in it, myself and my collaborators would be very happy to either help you get that integrated in some way so that everyone else can use it, or you can submit issues. We might get to it sooner or later. If you really want it to happen quick, you can develop it yourself.
It's open, you can do it.
Yeah, exactly. Everyone can use it. We want you to use it. We want you to find all of our bugs.
Awesome.
Yeah.
All right. So let's do a little result here. So
right. So figure one was just honestly something that we wanted to point out very quickly because we realized that folks hadn't really been thinking about astrometric binaries so much with Gaia yet. And so one of the things that comes up when you're looking for these compact object candidates in binaries is people immediately want to look to the luminous companion. In this case, it's a giant star for 2M0521, and you want to get a Gaia distance. And for most of the types of systems that we could produce out of our population synthesis, we found that the projected semi-major axis of the giant star, like its astrometric wobble, is in some cases much larger than the parallax due to the distance itself. In other cases, it's much smaller, but in most cases, you really need to pay attention to the binary motion when you're trying to sort of understand what you're dealing with when using Gaia distances. So it was sort of mostly a caution. And specifically, you can see for 2M0521, the fits that we took from Todd Thompson in everyone's paper puts it to having a significant amount of binary motion that should be added into whatever Gaia is measuring. So if you're interested in astrometric binaries, be very careful until Gaia gives you the fit with the binaries on any sort of distance measurement that you're trying to get.
Yep, fair enough. Got it. Yep.
Yeah.
Cool.
Yeah. So then for the rest of the paper, we sort of distinguish, you can see in section 3.2, we distinguish between just compact object plus giant stars and then compact object plus giant stars that are very similar to this specific giant star that was found, 2M0521. Since population synthesis isn't so great at reproducing a singular system, like that's definitely not what we're shooting for. If somebody tells you that they can absolutely reproduce it, they're probably a little bit too confident in their simulations, I would say. So the things that we were mostly concerned with is matching the general properties of a 2M0521-like system. And so in this case, we thought of it as, number one, we know that it's not filling its Roche lobe. So we wanted fully detached systems, no Roche overflow. We required that the orbit be circularized. And we wanted the effective temperature and surface gravities to match for the giant stars, because that's not so difficult to match in our stellar tracks. And then we just put a blanket radial velocity cut saying that we have to make it be consistent with the radial velocity, assuming the most, I don't know if it's optimistic or pessimistic, but assuming sin I is equal to 1 or less. Yeah. So it's a physical binary, the radial velocities roughly work out. So if you distinguish between those two things, the first thing that we find is, number one, there are not so many 2M0521 like compact object binaries that exist out there. However, in figure 2, you can see they do have a pretty similar formation scenario. In particular, we find that something that's going to produce a 2M0521 like giant star with a black hole companion has the black hole companion go into a common envelope. So the black hole progenitor here is the common envelope donor. This happens when it's on core helium burning.
Yep.
In its stellar evolution phase. And if you're a neutron star companion, you're going to go into a common envelope from the AGB phase. So that roughly works out mostly just based on requiring the giant star to be a giant star at present. The types of companions that you get require a certain age, and then you can sort of back that out, like, okay, black holes that have the right orbital period that come out of a common envelope have to go into it on either core, on core helium burning. So this isn't really a surprising formation channel at all, but it is nice to see from our simulations that we basically get the same formation for every 2M0521 like system.
But even after the common envelope evolution and such, they still come out to be a wide binary.
Yeah. Yeah.
They're not tight binary.
Right. So, and the one thing that I actually have been kind of spreading around as one of the main results here that sort of deviates from distinguishing between rapid and delayed is actually that black holes and neutron stars with giant companions that are observed by Gaia, so in like day to year long orbits, okay, every single one that we simulated was a post common envelope binary. So this is sort of a new class of post common envelope systems from high mass progenitors. Certainly the types of post common envelope binaries that I had been thinking about prior to this were these sort of like baby low mass, white dwarf plus main sequence systems. And these are super tight, like sub-day orbital periods. You really have to, the common envelope is extremely efficient to produce these. And this is totally different parameter space that we're dealing with here, because you've got, at least 20 solar mass star that's going into a common envelope. It's got an enormously puffy envelope. That envelope is probably not as bound to the core, so it's easier to expel it. But yeah, so I think Gaia really is about to lay some really awesome post-common envelope binaries down on the table for folks to start comparing to. and kind of spread their focus from just the white dwarf post-common envelope binaries.
So is the result you just mentioned, is that fairly robust with respect to the common envelope efficiency alpha that people use for that?
Yeah, so I would say no, not at all, because we didn't vary our common envelope prescription. So that's definitely something that I am certainly proposing to work on for the next few years.
We'll get to the future here.
Yeah. So we can talk more about that in the future section of this. Okay, so the real punchline, I would say, for the rest of this paper is in the next figure down. So this figure is relatively complicated, figure 3. So we'll go through it very carefully because there's a lot on there. Apologies to people for that, but we wanted to pack a lot in here. So on the y-axis, this is your compact object mass. And on the x-axis, we have giant star mass, and then we have our 2 rapid and delayed models. So there are 2, in each plot, there are these gray contours. These gray contours they are the result of all compact object plus giant stars that come out of our simulations. And it's the 1, 2, and 3 sigma contours in like increasing darkness.
Got it.
On the left, you see the delayed. There's a tiny little gap because our 3 sigma contours didn't make the neutron stars and the black holes meet up, but you can kind of see that there are 2 large gray swaths, and the neutron stars are in the lower compact object masses and the black holes are in the higher. And there's a very obvious mass gap between rapid and delayed.
Definitely.
So that's one thing that, of course, is no surprise. That's by design. That's what we put into our models. The blue points are the result of 500 realizations of the Milky Way. So we sample from our population to generate a population of binaries today. And then we pick all of the systems that have 2M0521-like features, and we plotted all of them to show you sort of the range. So this may look like there are a lot of 2M0521-like binaries, but there aren't.
Right, so I was gonna ask that actually. So how many realizations do you need to do to get this many to plot?
Right, so the plot is the result of 500. So 500 realizations.
Just by eye, I'd say there's at least 100 dots on that plot.
Yeah, there are. So there's something like between 0 and like 13 or so black holes per realization that pop out, and there's way less than 1 neutron stars that pop out. Yeah, each time.
Okay.
Yeah. So one thing to note immediately is that the number of 2M0521 like neutron star plus giant stars there's basically none of them. So from our models, we're finding that it is much more likely for this compact object candidate to be a black hole.
Sure.
And that's largely because of our radial velocity cuts. So there's this little blue swath in the lower right hand, and that is the result of requiring the radial velocities to match with sin I less than or equal to 1.
Okay.
So that's what knocks out the vast majority of our neutron stars. So the sort of final result here is that when Gaia launches, Gaia already launched. I'm used to talking about Lisa. When Lisa launches is usually my way of speaking. So when Gaia gives us the data, like the actual binary fits, included in that fit for 2M0521 will be an inclination. And that inclination measurement could either be a nail in the coffin for the rapid model, or it could be whatever. Maybe both of them work. But if there is an inclination measurement of a compact object with a mass greater than 3 solar masses and an inclination of sin I close to 1, the only way that you can make that is delayed.
Yep.
And so that will completely knock out the rapid prescription for people who use population synthesis. And that's actually pretty important because the rapid model is what a lot of folks right now are using to predict gravitational wave progenitors and also, I guess, just like merger products. So merging binary black hole, merging neutron star rates are often computed with this rapid model.
Right. So that constraint would at least apply to the 2M05121 type systems.
Yeah, but in principle, it would apply to everything.
Understood.
Yeah. So you should, the dream of a population synthesis person is being able to explain everything, right?
Yeah, absolutely.
So maybe by the time I'm, I don't know, tenured or something, we'll have ruled out like 3 models, and then hopefully people way down the line will actually have something that can consistently produce everything. But
love it.
we have to make baby steps.
That's right.
Yeah, so the last figure is really just numbers. As you can see, the number of 2M0521 type systems is just really low. However, the number of Gaia detectable black hole plus giant stars or neutron star plus giant stars is quite high. This bodes very well for Gaia in terms of finding compact objects and discovering them, and also because it's astrometry, actually giving us really fantastic characterization.
Okay, I need to actually look at the caption. Okay.
Yeah, so top row is low numbers, bottom row is bigger numbers. Yeah, that's basically all of the punchlines here. So the 3 short punchlines are, oh, actually, I was gonna leave this out, which is not very fair to the X-ray folks. We also pointed out that if you take standard Bondi-Hoyle wind theory, it's very standard. I will say that we assumed a very slow wind here, which gives you higher X-rays. So you might consider this as very optimistic for X-rays. This type of system is actually a sort of a X-ray luminosity puzzle, because you would expect to see X-rays accreting from a giant star under our standard wind assumptions. If you make the winds a little bit faster, that'll decrease your X-rays. But if you look at figure 5, that doesn't really, I mean, you're going to really have to decrease them by like 5 orders of magnitude. So we probably don't understand accretion efficiencies particularly well. And this is a really nice test case to sort of hit with things like Chandra. Yeah, basically things like Chandra.
And from this plot, I would say that delayed versus rapid doesn't really give you a discriminant.
No, not at all in X-rays. Definitely for discriminating between delayed and rapid, you really need a mass measurement. And that's what astrometry should give you. Yeah, and the other thing, I guess, to really be excited about with this is that as E Rosita continues to observe, you know, there should presumably be quite a few hundred of these types of systems out there for E Rosita to be picking up.
Which will lead us nicely into the future. It would seem like that's one direction for the future. I think you've mentioned a few others.
Yeah.
Near and far term.
That's right.
Evolution.
That's right.
But you know, sort of globally, what do you see in this field coming over the next couple of years, sort of as a community, right? So where do we go as a community, given what you've published already?
Right. So I would say that this is one tiny appetizer of the deluge of data that we're about to get from Gaia. If I'm out at pubs with friends, I will very excitedly say that the future of Gaia is binaries. I think that...
well, I think you just said that in a non-pub environment. So
I know I did. I'm still that excited about it. No, but for real, like I think that the type of data that you can get from Gaia is a totally untapped resource, and people who are modeling things like mass transfer efficiencies, common envelopes, compact object formation, all of these types of things, usually we're constraining these types of things with gravitational wave observations, and that's fantastic because we have gravitational wave observations, we should do something with them. But you're sort of, oh, sorry, say again.
It's a small fraction.
It is tiny, and like we're constraining exams, we're constraining a gravitational waves, and then there's a lot of uncertainty in the middle. And things like Gaia are really going to transform the types of constraints that we can make on binary evolution, because we get really fantastic constraints on things like masses, orbital periods, like the dynamics of the systems. Working along with Gaia, I think the other thing that's really going to revolutionize this is radial velocity surveys.
Okay.
Because they sort of pick up, like if you think about trying to constrain binaries across just like orbital period space, you can start really tight with gravitational waves. You take a step back, it's X-ray binaries. You take a step back with radial velocities. You take one more step back, and then you're into astrometry.
Yep.
And so the next decade or so, I think we're just going to be bathing in binary data, and hopefully we'll be able to say something like positive about binaries.
I love that phrase, bathing in binaries. That's awesome. That is a great.
Yeah, it's a good time to be a stars person, I think.
Absolutely. Well, sure.
That's great.
I'm biased, highly biased though.
Yeah.
Very cool. Katie, I want to thank you so much for sharing your time with us and for walking us through your fantastic new paper there and sharing us with a little bit where the future goes. I will be putting Katie's link to the paper, a link to her Katie Loves Binaries website that you can check out. And I think she's already indicated that it's perfectly great to contact her, particularly with regard to the cosmic pops in, or about the science itself that something like Cosmic can enable. So.
Absolutely. Thanks so much for having me. I hope everybody enjoys reading the paper.
Awesome. Thanks, everyone. Bye-bye, and we will see you on the next one, and I will do a